Thank you. I'm Alison Snyder. I cover science and oversee our world news coverage at Axios. And, fusion is a topic that increasingly comes up in both areas, especially with the field's scientific advances over the past few years, but also, China's increasing capabilities and ambitions in the technology, and all of that against a sort of backdrop of growing energies from big tech, global warming, and the sort of effort to mitigate its effects by producing clean energy. So I'm really excited to talk today with Brandon Sorbom. He's the co-founder and chief science officer at Commonwealth Fusion Systems. He is the main driver of the company's scientific direction and R&D efforts, and leads the company's efforts to advance the design of their commercial fusion power plant, ARC. Do you call it ARC or ARC?
ARC.
ARC. All right. Yeah. So thank you for taking the time to talk with me today, Brandon.
Yeah, thanks for having me here.
Yeah. So listen, there's been a really dramatic increase in private investment in fusion energy over the past few years. I think somewhere I saw a statistic of about private companies raising, at least $7.1 billion. And then there are public investments too. China outspending the US this year, $1.5 billion to $750 million. So I guess the big question for us today is, will and when will fusion energy change everything and deliver on that investment? So maybe a good place to start is, what's the sort of list of things that has to happen for this to get to commercialization in terms of the actual machines, the systems?
Yeah. So the first thing that has to happen is we've actually already seen the break-even point be demonstrated. A couple of years ago, there was the really exciting announcement from NIF, the National Ignition Facility out in California. And so they showed that you can, they had proof that you can get above a break-even point. And we knew this was possible, theoretically, and this is the first device to do that. But I think the next step is to do that in a commercially relevant device. It doesn't necessarily have to be in a device that is making power going out into the grid, but getting that break-even point, we call it Q greater than 1 for gain, in a commercially relevant device. And so that's what ourselves and several of the other startup companies are aiming for right now, is to build this first sort of demonstration device. And then after that, building the first truly commercial power plant that would be on the grid, putting electrons on the grid that come from the generation of fusion energy.
So just for a second to sort of lay the stage, I guess, what's the sort of broader ecosystem in terms of the number of companies, the different concepts that are out there, just to give us a lay of the land?
Yeah, so it's pretty big. So there's, as far as companies are concerned, it's grown substantially. Like you said, that $7 billion of investment, if you had looked like 5 years ago, it would have been a small fraction of that investment. It's really in sort of the last 5 or 6 years that there's been this growth of in the private sector of companies pursuing all sorts of different concepts on how to get to fusion energy on the grid. And so I actually don't know off the top of my head right now. Feels like there's a new company every month or two, but there's several dozen companies all around the world. Many of them are in the US, but this really is like an international thing that's happening. And like you mentioned, so far, just over $7 billion of investment has been raised in the space, which is pretty incredible. And I think that really speaks to the maturity of the technology. And so fusion, if you had asked, maybe 5-10 years ago, who are the players, it would almost entirely be academic labs. It would be big national labs. There's a very large international collaboration called ITER, which is being built in the south of France right now. And that was really the biggest game in town. And now there's a whole bunch of private companies that are aiming to do this in a commercial way, and basically building upon what our strategy is, to really build upon the work at CFS of this concept called a Tokamak that most of the world's academic communities have been focused on. So there's other companies out there that are looking at alternate concepts that don't have as much, I would say, there's not as much of a scientific backing in the community, but they're looking at these concepts as a way to maybe try to get something faster and explore unexplored areas of the space. Because there's many different ways that you could get to a fusion plasma.
So, but early enough that those are still in the game, right? That those are equally, plausible, possible?
Well, I mean, I'm obviously a little bit biased here. I would say that what differentiates us is that the science that we're building on is, I would say, arguably the most rigorously proven out in the community. But there are other people that are out there, trying other concepts and publishing on their results, and really subjecting them to the rigor that our concept has been subjected to already in the academic community.
Right.
And I think the main point with the startups is that there's this mentality of being able to have very fast cycle times. I mean, it's very traditional startup mindset, but it's being able to fail fast and being able to go in multiple iterations of something. And I think that's really the beauty of this whole startup ecosystem, is that there's people trying a bunch of concepts, and some of them might be very far away, but I think it's good that people are trying things, and putting the results out there so that we can see if something works or not.
So I've often heard it described as it's not so much about like whether it will work, but whether it'll be cost effective or cheap enough to actually make a difference on the grid. And so, in other words, the tech might work, science might work, but will the economics? Do you agree with that? Is that a fair assessment of things? I mean, I want to go back
I don't think
some of the technological things too, but yeah.
I in my mind, I don't think it's a question of if it will work. It's a question of when it works. And then, like you said, it has to be economic and it has to work for people. And so again, with our concept, we looked at where the science was going and where things were going, for example, with ITER, which is a very, very large device. And we said, that doesn't really scale to something that looks like it could be economically feasible in today's current environment. And so we said, and all the other startups have basically said, you have to build something that is small enough that you could build this with a single company or a single entity that could build this. And on a time scale, it has to be small and it has to be fast, right? You can't build something that's very large and takes a long time and have that be commercial. For ITER, that's not a problem because it's a science device. So ITER does not necessarily have a commercial mission. But in order to get fusion energy onto the grid, we do need to get to that step where we are building devices that are small enough that the capital cost of the device is low enough, and that the time to construct is short enough that you could actually make a case for these being economic. And I think we have a really clear path to that. One of the beauties of fusion is that the fuel is effectively free. The fuel is coming from isotopes of hydrogen, one of them that's extremely plentiful, and the other one that you can generate from lithium, basically. And so the feedstock is effectively free, and actually even going a step further than that, you can put all of the fuel basically for the entire lifetime of the plant on site on day one. So there's not even necessarily like a fuel distribution in steady state. You distribute the fuel to the plant once, and then you start it up. And so that is very, very favorable to your operating economics of the plant. And I think, the name of the game right now is to get the capital costs of the devices down to a point where that also makes sense. And we think we have a pathway to do that with our technology and shrinking the size of the device down to a scale that makes sense. And so, you're building something that's like the capital investment of a natural gas plant, but you don't have to pay. There's not this huge operating cost of paying for this fuel source that has to be, you have to pipe in a ton of fuel, and it doesn't have the negative externality of putting a bunch of carbon into the air.
Right. So you just answered my next question, which was about how small, when you say small, and then, but how fast? How fast are you talking about?
To get to commercialization?
Yeah, what's needed to be able, you say when you have to be able to, yeah.
So we want to get to commercialization by the early 2030s. Mm-hmm. I think that's the speed at which we want to do this. And I think in order to, that's like the first plant. And then we need to get this to where you're able to build a plant in 3 to 4 years. So similar time scale as building a natural gas plant, for example, where you go from getting a site to having something connected to the grid, producing electrons into the grid in 3 or 4 years.
Okay. So in terms of like what's needed to actually build these, and sort of the supply chains that are necessary, what I guess, where does it stand today, and where are you headed? And then we can talk about all the things that will take to get there.
Yeah. So the supply chain is a really interesting piece of this. It's there are some specialty components that are in the different concepts. So, for example, ours and several other of the startup companies utilize something called a superconductor, which is a material that can pass current through it. It's basically like a very, very good wire for making magnets. And it's a wire that when you get it cold and you pass current through it, it does not heat up. So like a normal wire, like, in an old style, like incandescent light bulb, you put wire through a filament and the filament glows red hot, and that's how you get the light out of it. And any normal metal that you do that to, you'll generate a whole bunch of heat. And so you can't build a conventional magnet that would be anywhere near economically effective on a power plant. You'd basically have to take more energy running your magnets than you would get out of the plant. But if you use superconductors, then there's actually zero resistance that's in a superconductor when it's in its superconducting state. And so there's no power dissipation in the superconductor itself. And that actually makes the magnets, that drops the power consumption to nearly zero. You have like a tiny, tiny bit going into like the leads from your power supply that go into the cryo system of your magnet. But it drops it substantially to the point where basically you can get all of the energy that's being made from fusion and take that and transfer it out into electricity.
Mm-hmm. What are some of the other, I guess, potential uses of take that technology, for example, as it's being developed, or, are there knock-on effects?
Yeah.
Yeah.
Yeah. So the superconducting wire is really interesting because we use it for magnets, but really you can think of anywhere that you use wire. You could think about replacing it with superconducting wire. So one of the big markets for this that are suppliers of this material is called HTS. I'll try to refer to it as superconductor, which is more general. If I slip and say HTS, that's what that means. Our superconductor suppliers are looking at like transmission markets, because right now transmission lines have these same losses, and there's been an optimization done to try and limit the losses as much as possible. But at the end of the day, there's still a decent amount of loss on transmission lines. And so there's actually startup companies out there right now who are trying to build transmission lines that would be lossless, built out of the same superconducting material that we're using for our magnets. You could imagine this going into MRI magnets. That's another big application that uses magnets. But really, anywhere that you have wires, you could think of like, replacing bus bars inside of factories and things like that. Grid interconnects is another place that's kind of along the same line as power transmission. But there's a whole bunch of uses for these superconductors that are really interesting.
Have there been any spin-offs to date, I guess, from the development of some of these technologies, or not yet?
Yeah. Oh, yeah. I mean, like for the trends, I'll call them out. But there's, just in our area, there's a company that we work with called Veer. That is one of the companies that's working to commercialize this technology into transmission lines. And there's a few other companies that are also looking at this. And one of the things that is really interesting, I think, about fusion is that for these superconductors have not really been, the high temperature ones that we use have not been around for a long time commercially. But people have known about the material itself kind of in like a sort of like a lab scale for 30 years. And so people have dreamt about what we could do with this. And what fusion is doing is it's really an enabling technology for our magnets. And so we took that supply chain, and we're very much driving that supply chain right now to increase their volumes and to decrease their prices. And as we do that, that's opening up all these other markets that maybe would have been, more of a marginal cost increase if there hadn't been someone to take that initial step and say, okay, get the volumes high enough and the price is low enough that you can now start having it be economic to use for other things like transmission lines. There's other people who want to look at using it for motors and generators. If you make the windings of the motors and generators superconducting, you can make them more efficient and weigh less. So yeah, there's some really interesting spin-off technologies that you could get, and we see that sort of around. We're starting to see that in different places around the supply chain, where things that fusion is driving can benefit other industries. And also we see things on the flip side. We see things like like solid state power electronics. Our devices, the Tokamak, is basically, it's actually really interesting. The Tokamak itself does not have very many moving parts. The tokamak itself is actually, there's no moving parts inside of the tokamak. And you can almost think of it as it's almost like a solid state device in of itself. But the magnets are driven by power supplies that have solid state electronics. There's RF energy that goes in that we actually are using solid state to drive that now instead of tube based. And so that's an example of us taking a technology that was developing elsewhere and incorporating that, taking advantage of those technological trends in the supply chain and using them to ultimately make our device more economic.
Right. Are there, I know earlier we were talking about how there's a couple of different approaches to this. My understanding is all of them need sort of, technological developments in materials, different types of, parts. Do any of them overlap in the sense that like a material that's built for one approach, is it potentially could be useful in another? Just thinking about that supply chain. Yeah. Okay.
Oh yeah, there's definitely a lot of synergies. I mean, I think in general, having strong structural steels, especially for the companies that make magnets that can operate under cryogenic temperatures very well, that's something that scales. All of these devices, require large machined metal structures. I guess I shouldn't say necessarily it doesn't have to be machined. They require large metal structures. So being able to machine those structures, having the supply base to be able to do that, or maybe in the future, doing more advanced manufacturing techniques to make those structures. That's something I think that benefits the entire industry. For the ones that use magnets, the superconducting supply chain is of course very important. And I think the solid state is another area where advances there would really benefit most of the companies that are building concepts right now.
And so aside from the supply chain, what about, I guess, talent? How important is there a talent pipeline in terms of not only scientists, but also like, I don't know, pipe fitters, welders, machinists? And is that an interim need while you're sort of, there are these bespoke machines and pilots being built, or is it a much broader need for the industry?
I mean, I think it's a long-term it's a long-term thing where we want to build up a talent pipeline. I will say that one of our strategies has been when we design our machines, we try to do it with using as little bespoke nature objects as possible, right? Because we want to be able to take advantage of existing, welding capability and pipe fitting and make this thing look as much like a conventional power plant as possible, so that you can utilize as much of the existing workforce as possible. And we've actually had, a good example with this is our constructors who are building the Tokamak Hall. So that's the building that houses Spark, which is before ARC, we're building this device called Spark, which will be the first commercially relevant net energy, but it's not going to put electrons onto the grid. And, the people who are building, the constructors who are building this building for us, it's a somewhat specialized building. You have to have, there's concrete in it, has some special rebar in certain areas. But for the most part, it's a conventional, it's using conventional building using conventional methods. And so we didn't have there's not like a special construction firm that knew how to build tokamaks. We actually partnered with a local constructor, Bond, which we basically sort of taught them how tokamaks work, and they taught us how construction worked. And we were able to get them up to speed very, very quickly to build a structure that suited our needs. And I think, doing that in as many parts of, both the infrastructure that you need to run the plant and then the internals of the plant itself is going to be really important so that we can scale this as fast as possible and utilize, like you said, as much of the existing workforce. I do think, that being said, I do want to add that there are, we still would like to see, I would personally love to see more fusion programs in not just graduate studies, but in undergraduate studies, just to get people, familiar with the ideas. And to build that talent pipeline. I do think that, we want to scale the industry exponentially. And so I do think we need to scale, we do need to scale sort of the fundamentals of, the physics behind fusion and things like that in schools. But it's not something where we need to retrain every single aspect of how you build these plants. That's definitely not the goal. The goal is to be able to reuse as much sort of existing knowledge and existing infrastructure as possible. Because it really does come all the way back to economics, like you said at the very beginning.
Right. I've also heard the fusion sort of described as being on par with AI in terms of the potential return on investment. so if I get might as well ask how the two sort of come together. Are there opportunities for, or are there ways in which AI is already impacting the work that you and the broader sort of ecosystem of fusion energy companies do? Yeah.
Yeah, I think it's actually, yeah, it's twofold. It's impacting us in two different ways. In one of the ways, and I think we're probably just the tip of the iceberg on this. We do use, there are some applications of using AI, like people, this is more in academia right now, but we're reaching out and working with these groups about using AI to basically get a deeper understanding of the physics behind how the plasmas work, and to look at basically predicting events in the plasmas that might cause them to become unstable and disrupt. Not from, and I should add, not from a safety point. So fusion is extremely safe, but if the plasma disrupts, then the plant, there will be a blip in the output. So you don't want that to happen. And so AI is being used. AI techniques are being used to look at making the operation more stable. But I think really more importantly on the other side, I think AI is really affecting fusion because it's driving growth in demand for energy, right? All of these data centers that are powering all of the AI tools that we use are using massive amounts of energy, and all of the technology companies that are building these are, they all see that we need to find a way to power these, and it would be really bad if we built a whole bunch more coal power plants to power these AI data centers. We would like to power them with something clean, and I think fusion is a really, really good option for this because unlike solar or wind, which are great in their own right, for a data center, you want 24/7 power. And so if you want 24/7 power with something that's also clean, fusion is one of the few options that you have to be able to do that. And it doesn't have the same safety considerations that you would have with nuclear fission. Which you have to, there's a lot of safety considerations around that. And fusion is inherently safe. And so fusion would be a very good option to be able to, to provide clean power to these data centers in a way that does not, disrupt the environment.
Are there any big tech fusion partnerships that you think are important to watch or that you're aware of?
I think, I think it'll be important to keep an eye on. A while ago there was an announcement. One of the companies in the ecosystem announced an agreement with Microsoft, and I think looking for more things like that, will kind of be a signal that the tech industry and AI is taking a look really seriously at how to actually power these data centers with clean energy.
Mm-hmm. Do you, you just mentioned fission, and I wanted to go back to that actually, because what are the sort of, I guess, regulatory hurdles or considerations that you see, potentially popping up as this progresses? And well, we'll start there.
Yeah. So I think that we definitely looked at regulation and we said, okay, we need to be regulated different from fission, because I guess I should back up. Fusion is inherently safe. When I say that, it's not like we build something special into the process to make it safe. It is just from like a fundamental physics standpoint, fusion is inherently safe because it actually is the fusion reactions that are occurring are actually very fragile. It's why we don't have fusion yet. It's kind of a double-edged sword. You would imagine intuitively that if you're basically creating a star, because stars use fusion, stars are big balls of plasma that have fusion, you would think that it's this big hot thing that's like lava that, if it hits the side of a container, then it would be really bad. But actually, they're very diffuse. And so if you were to lose confinement on your fusion plasma and it drifts and it hits the wall inside of the vacuum chamber that it's in, it extinguishes itself. And so you're actually doing the game of fusion is all about trying to protect this plasma from its surroundings, which is a challenge engineering wise, but it also makes the system inherently very, very safe. If there's ever, if there was like a rupture in the containment vessel with the plasma, then the machine just shuts itself off. And so, because of that, we said, well, we need a different regulatory regime than fission, because that's very different than fission, where it's the other side, where you're trying to control this chain reaction and make sure that you don't have a chain reaction that runs away. And we said, okay, we need a different regulatory scheme than fission. And we actually, in the United States, we have that now. So the NRC, the Nuclear Regulatory Commission, um, passed guidance, which has actually been codified into law now, that regulates fusion similar to particle accelerators, which is really more the case that the fusion devices operate more like particle accelerators, where they do make instantaneous radiation, but it turns itself off. You shut the switch off and the device turns off immediately. And so I would say we have a much more favorable regulatory regime than, a couple of years ago, it was unknown how we would be regulated. And it would have been a really big mistake to regulate like fission, because it's just the inherent characteristics of the system are so different.
So, two more questions.
Yeah.
One is, so you have all these, growing investments, you have advancing technology, and yet you sort of, oftentimes fusion isn't included in some of the predictions for electricity generation, right, over the next, 25 years. What do you think is the case for getting it in there?
I think it's a lot sooner than people think it's going to be. I think the case is, you can look at the growth of the industry. Going back to even just, I know it's kind of a very general metric, but if you just look at where the investment money is going, right? People are smart, people are seeing this space really take off, and the investment dollars are pouring in. And I think that's a really good indicator that, I don't think it's necessarily a causation, it's sort of reverse, right? But it's an indicator that, that people are really starting to take this seriously. And, the people that invest in this are taking a serious look, at least in our experience, people are taking a look under the hood and saying, okay, like send diligence teams in, and see if this is for real, and then putting money into the space. And so we see that as a really good sign. And I think it's probably not going to be too long before you do see fusion in every single energy projection going forward. I do think, that probably this moment of demonstrating net energy in a commercially relevant way would be another catalyst for that. Although I don't think that at this point, I think there's enough people that have looked at the science behind it and said, yes, this is actually possible. And they've looked at the engineering challenge and say, yes, there's an engineering challenge, but we've done really, really hard things before. We sent people to the moon, like almost 50 years ago, right? And so like we're really good as a species at engineering challenges. And so I think people are really seeing that this space, there's a whole bunch of advancements that are happening, and especially going back to one of the really exciting things. Like I came out of the academic community, and we still as a company have a lot of ties to the academic community. But one of the really exciting things about seeing this go into the private space and in the startup space is you see these fast iteration times and these cycles, and you can just see the flywheel just continuing to turn, of people generating ideas, trying the ideas. Sometimes they work, sometimes they don't, but you keep that flywheel going and you can see the progress just picking up. And people are coming up with clever solutions for how to solve the engineering challenges behind the systems.
Great. That's a great place to stop, I think. Thank you so much. This is really interesting, and we really appreciate your time. So thank you.
Yeah, thank you very much. It is a very exciting time.